So the next talk is quantum simulation with ultracold atoms, Dr. Richard Fletcher. And I'll just mention this is following, oh, you're all set?
I'm good.
Okay. I won't mention anything.
Okay, great. Thank you very much. So my name is Richard Fletcher, and I'm one of the other first-year Pappalardo fellows. So I moved over to MIT from the University of Cambridge in the UK, and I'm an experimental physicist working with Professor Martin Zweerlein. And what we do in our lab is to take clouds of atoms, cool them down to very, very low temperatures, and then try to learn something about the behavior that emerges when you have many particles interacting with each other and governed by the laws of quantum mechanics. And why is this an interesting thing to do? Well, the universe around us is really made up of many-body quantum systems. And these appear over all sorts of different length scales, and they're notoriously rich in their behavior and difficult to understand. And one of the reasons for that was summarized by Phil Anderson back in the 1970s in an essay entitled More is Different. And the point Anderson was making here is that just because you understand how one or two particles behave doesn't mean you understand how a million will. And it's this notion of new phenomena somehow emerging from the collective behavior of many constituents that makes these systems both rich and difficult. And just to compound matters, the fact that the size of a quantum system or the size of the state grows exponentially with the number of constituents means that even computationally it can be very difficult to investigate these types of phenomena. And so both of these combine to mean that these systems are very challenging theoretically. And so what we do in our lab is try to construct simplified, very controllable playgrounds where we can manipulate these atoms and try to learn something about the quantum physics that comes out. And so to kick off the type of physics that I want to be talking about today, I'd like to begin by introducing this character, whose name was Edwin Abbott Abbott. And he was an English schoolmaster and theologian who lived in Victorian Britain. And in 1884, Abbott wrote a book, which is a little fictional novel, and it's entitled Flatland. And if we zoom in, we see that it's called Flatland, A Romance of Many Dimensions by A. Square. And in this book, Mr. Square, who's a citizen of the two-dimensional world of Flatland, goes on a journey through worlds of different dimensions and describes how different life can be when we change the number of dimensions that we live in. And so he spends a little bit of time in his native Flatland. He also visits Pointland, one-dimensional line land, and also three-dimensional space land, which is more familiar to all of us. And what comes out of this book is perhaps the obvious statement that the world can really look very different. And one of the interesting sort of points that comes out of the novel is how important the notion of shape can be in lower dimensional systems. And we have to remember that this book was written in the time of Victorian Britain when this notion of social hierarchy was a very, very important concept. And so it turns out that in Flatland, the position of a citizen within society is determined by their shape. And so right down at the bottom of the pile, you have these nasty, irregular isosceles triangles. And as we move up through society, the nobler citizens gradually gain more and more sides and become more regular, until up at the top, we have an aristocracy made up of many-sided polygons, and of course, right at the very top, circles. And so these citizens spend a lot of time trying to figure out the social standing of their neighbors, and for example, trying to develop ingenious ways of how to tell the difference between pentagons and triangles, because of course, in two dimensions, every shape simply appears to you as a line. And at one point in the story, our protagonist even visits one-dimensional line land. And there, I think, again, the point being made is about some kind of antiquated idea of social order. But here, the topology of being in one dimensions actually enforces how citizens are arranged. And so right at the center of Lineland lives the king, and on either side of the king lives his subjects. And of course, because you can never move through one of your neighbors, wherever you're initially positioned in this world is where you'll then spend the rest of your life. And so the point I want people to take away from this is that when we change from the familiar three-dimensional world into, for example, two, physics becomes very different. And what I'm interested in doing with our cold gases is asking how quantum behavior changes when we move from three into two dimensions. And this is an interesting thing to do for many reasons. One of those might be that the different behaviors that emerge in lower dimensional systems can have all sorts of important technological applications. And this is something that Sanfeng talks about in his talk earlier. And for example, there's been a lot of excitement over the last few years in graphene, which is where electrons move around in a two-dimensional sheet of carbon atoms. And it's also been speculated that the origins of superconductivity, which is when a substance begins to conduct without any electrical resistance, might lie in the way electrons move around two-dimensional planes of atoms within the crystal structure that make up these substances. But for me, the second point that's really the interesting one is that often by thinking about physics in unfamiliar new situations, forces physicists to develop new ideas and new concepts which can then be applied in all sorts of other areas as well. And just to give a couple of examples of this, out of experiments and theoretical work pertaining to two-dimensional systems came work that actually forced us to reconsider something as seemingly basic as what we mean by a phase transition. So how does one state of matter turn into another? And out of this work has also arisen this notion of topology and how important topology can be in determining the properties of a material. And this is an idea that first emerged in two-dimensional systems, but is now one of the real hot topics in modern condensed matter, and it's being applied to all sorts of materials, both in 2 and in 3 dimensions. And just to illustrate what I mean by topology and to talk about the kind of object that I'm interested in, what I'm showing on the right-hand side here is a fluid. And what's interesting is if this fluid was a quantum fluid, the laws of quantum mechanics mean that the rotation of this fluid, so how fast it's spinning, can only take certain discrete values. And the physical consequence of that is that if one has a rotating fluid, so it would contain, for example, a little whirlpool known as a quantum vortex, there's no way to smoothly unwind this motion. And what that means is that the presence of this vortex is somehow protected against smooth deformations and perturbations to the system. And so it's known as a topological defect in the fluid. Now, what I'm interested in are 2 of the really fundamental examples of quantum collective behavior. And the first of these is superfluidity. And this is the mechanism by which somehow, in a system of many particles, all of the constituents begin behaving as one collective object, and the fluid can start to move around without losing any energy either to dissipation or resistance. And if that fluid is charged, so for example the electrons in a metal, then what one is left with is a superconductor. And if that fluid is neutral, for example liquid helium, then what you get is a neutral superfluid which can display frictionless flow and display all sorts of remarkable properties such as climbing up and escaping over the walls of the container that it's held in. Now, one of the really interesting aspects of superconductivity is how it acts in the presence of a magnetic field. And we can already see from the pictures I'm showing here that something quite interesting physics starts to emerge. In the left-hand side, what we're actually seeing is a little superconductor hovering above the surface of a magnet. And somehow it's so strongly repelled, and it really doesn't want to be near the magnetic field, and it would rather sit up in midair than get anywhere closer to the surface. But it turns out that in certain situations, you can persuade a superconductor to accept a magnetic field. But what happens is that the field will enter the superconductor at certain specific locations. And so what I'm showing here is a picture of a superconductor, and every one of these black dots is showing a little bundle of magnetic field punching into the surface, and they form this beautiful lattice on the surface. Now, of course, in a neutral superfluid, such as liquid helium, magnetic fields don't play any particular role, but it turns out that completely analogous physics emerges when we consider the effect of rotation. And so there's somehow an interplay, or you can somehow map the effect of a charged particle in a magnetic field onto a neutral atom under rotation. And sure enough, if we take a cup of liquid helium and stir it, as you stir the liquid helium faster and faster, you gradually get the appearance of a lattice of these quantum vortices, these little rotational excitations, which start to populate the system. And so turning to the first of these phenomena, superfluidity is really the great paradigm of quantum collective behavior. And so somehow out of the complicated interactions of billions and billions of constituents emerges this beautiful, very simple phenomenon where the fluid starts to flow as a single object without dissipation. And so it's this macroscopic manifestation of quantum mechanics that makes it such an interesting phenomenon to study. And so for me, the question of how and when a system becomes superfluid is really one of the basic questions of quantum mechanics. Now, when we're talking about whether or not how a system changes from one state into another, what we're really asking about is phase transitions. And for a lot of the 20th century, physicists' views of phase transitions was dominated by Landau's view, which discussed them in terms of symmetry breaking. And that's perhaps a little vague statement to make, so I'd just like to clarify what I mean with a couple of simple examples. If we imagine a cup of water, the molecules in this water are really randomly arranged in space. They're moving freely around, and there's nothing special about any one point in space. Now, once this water freezes into ice, these molecules have to adopt a regular lattice, and this lattice needs to choose a particular point in space to center itself on. And so we can say that freezing is associated with the breaking of some translational invariance, breaking some symmetry of the system. And another familiar example will be magnetism, where in an unmagnetized metal, the little magnetic moments are all pointing in some random direction in space, and once we cross some transition, they all spontaneously choose some direction to point in. And so again, you can say that magnetism is associated this time with the breaking of a rotational invariance. And so for many decades, physicists always tried to classify phase transitions according to what symmetry was being broken. Now, when we then consider a two-dimensional system, this leads to some very interesting conclusions. And that's due to a very famous theorem which tells us that ordering is actually forbidden in Flatland. And what this means in practice is that if we take a two-dimensional gas or two-dimensional fluid and ask what the fluid is doing at two well-separated locations, the behavior of the system on the left-hand side will always be uncorrelated with the behavior of the system on the right-hand side. And the presence of thermal fluctuations and excitations in the system will always scramble the correlations between these 2 points. And so at first, it's not clear how some kind of ordered state like a superfluid can emerge. But what's quite remarkable is if you cool such a system down, you do indeed find a transition to a superfluid state. And the basic picture of this is that at high temperatures, this gas is full of all sorts of excitations. And in particular, it's full of these quantum vortices, these little rotational defects which keep cropping up. And as we cool the system down, below some critical temperature, these vortices become energetically suppressed. And so what you have is a situation where this gas of topological defects disappears from the system. And so there's therefore some change in the topology of the fluid. And what's remarkable is that this change in topology and the disappearance of these topological defects is sufficient to drive the fluid from normal at high temperature to superfluid at low temperature. And it's a really important point to stress here that no symmetry is being broken. So this transition doesn't fall into the usual categories of phase transitions that physicists were so used to. And this is known as the Berezinski-Kostelis-Thouless, or BKT transition. And the early theoretical work that led to the discovery of these types of phenomena was recognized with the Nobel Prize in physics in 2016. And so when we're asking about whether or not a particular system will become superfluid, it's obviously very important to ask what type of particles constitute the system. Now, particles in nature fall into two categories. Some of the particles, like photons in light and certain atoms, will be bosons, and some of the particles will be known as fermions, which are, a famous example would be an electron. Now, bosons are very sociable, and they really like to get together, and they're very happy to share the same quantum state. And so a couple of nice examples of phenomena that occur in bosonic systems would be a laser where many photons of light all start to occupy the same mode of an electromagnetic wave, or the famous Bose-Einstein condensate, where many atoms in a system will all start to accumulate or condense into the lowest energy state in a quantum system. And so somehow this notion of bosons wanting to be together really lends themselves to forming a state like a superfluid, where somehow many constituents start to behave as a single object. Now, when it comes to fermions, the picture initially looks very different, in that fermions are really intrinsically antisocial, and they refuse to occupy more than one fermion per state, and instead they'll gradually fill up one fermion per state of our system. And so initially, one feels that maybe how are we going to reconcile this picture of fermions with the possibility of something like superfluidity? Maybe that's actually a bosonic phenomenon. But quite remarkably, nature gives us a way out of this quandary. And the way out is the realization that fermions aren't really intrinsically antisocial, they're just shy. And so whereas individual fermions will refuse to all occupy the same state, if you give them a chance to find a partner, then they're happy to go along to the party. And so if we take a system containing two types of fermions, if these fermions are allowed to pair up, these pairs can then somehow start to act as a single collective fluid. And so this notion of pairing is very, very important, and it's how a phenomenon such as superconductivity arises in a system of fermions, such as electrons in a metal. Now, in ultracold quantum gases, we have a really remarkable opportunity. And that is that because of the fact we can tune the strength of the interaction between our atoms, we can persuade our fermions to really pair up however we like. And so we can either ask them to form tightly bound molecules, and these molecules really behave as composite bosons. And so a gas of these paired fermions behaves simply as a gas of bosons. They don't notice their underlying fermionic nature. And then we can make some continuous transformation and persuade this gas of bosonic pairs to somehow change its nature and instead form a gas of fermions which instead are paired in momentum space. And these are known as Cooper pairs, and this is the mechanism of pairing which occurs, for example, in a superconductor, when these electrons will pair up, form Cooper pairs, and then form a superconducting state. Now, in quantum gases, we can actually tune this crossover continuously. And so I think looking into 2 dimensions, it's a very, very interesting question how to combine these notions of BKT superfluidity, which somehow mediates a superfluid transition in 2 dimensions, and these notions of topology, which play such an important role, with the essential presence of different natures of pairing in a fermionic system. And so this is the system, one of the systems that I want to be studying over the next couple of years here at MIT. And so having discussed superfluidity a little bit, I'd like to say something more about the second ingredient that it's very interesting to add, which is that of magnetic fields. So as we've already mentioned, the presence of a magnetic field has really profound effects on the behavior of a superconductor. And in particular, the magnetic field can enter a superconductor at these well-defined points indicated by these little black spots on the surface. Now, we want to understand something about this type of physics, instead using our very controllable neutral atoms. And so the question arises of how can we simulate this type of physics without charged particles, instead using our trapped atoms, which are neutral. And so I've already alluded to the answer earlier in the talk, but we can make use of this equivalence between the motion of a charged particle in a magnetic field or a mass which lives in a room which is spinning. And so this can be seen by looking at the equivalence between the Lorentz force, and this is the force that a particle of charge q, moving at a velocity v, feels in a magnetic field of strength b. And the Coriolis force, which is when a particle of mass m, moving with some velocity v, is living in a world which is rotating with some angular velocity omega. And it doesn't really matter what the actual form of these equations are. The point is that they're really completely identical structures. And so I'm simply switching one letter for another. And what that means is that the same physics that gives rise to electrons following a curved path when subjected to a magnetic field gives rise to the circulation of weather patterns on the surface of the Earth. And this immediately tells us how to proceed. If we take our trapped cold gas of atoms, send in a spoon, which in our case would be a laser beam which exerts some force on the gas, and stir the cloud, what you in fact observe is this beautiful lattice of rotational vortices. So here rotation is playing the role of magnetic field in a superconductor. And so there's been a lot of beautiful experiments done on this, in particular here at MIT, but these were all restricted to the regime of relatively low rotation speeds. And so one of the things that we want to address in the next few years in our group is what happens when you go to much, much higher rotations. And what I mean by higher rotations is a regime where you have, on average, one of these vortices, or roughly one of these vortices per atom in your gas. So it's a very, very strange state of matter, and in fact, this would realize a completely new regime in physics, in that it's simply not possible to rotate a cup of liquid helium, for example, so fast as to reach that limit. So there's a lot of theoretical excitement and a lot of theoretical uncertainty of the type of physics that will uncover there, and so I think cold gases offer a very, very nice opportunity to explore this new frontier. And so just in the last few minutes, I'd like to tell you a little bit, having discussed the physics, to tell you a little bit about the actual systems that we're working with here. So as I've already mentioned, we take a gas of atoms, we cool it down to very, very low temperatures, and we try to understand what's going on. And really one of the big selling points of the field is that we have an extremely good experimental handle over almost every aspect of the gas's behavior. So we can play around with the confining geometry or the dimensionality that the atoms live in. We can tune the strength of interactions or density. We can subject them to artificial magnetic fields, as we've just seen on the previous slide. And so having all these different experimental knobs make this a very, very nice quantum playground to try to understand the type of behavior that emerges in a many-body quantum system. Now, as a little bonus feature, as well as having all this experimental control, the densities of our clouds are roughly 10 billion times lower than in a conventional system that you'd find around us in this room. Now, this confers two advantages. And the first advantage is that generally theoretical descriptions become a lot more tractable. And that means that in cold gases, you can often make a much more direct comparison between a theoretical prediction and an experimental observation. And the second advantage comes from when we consider the types of length scales and time scales over which physics can take place. And so in a typical condensed matter system, which is made up of atoms bound together and electrons moving around between them, the shortest distance over which physics can happen is really set by the interparticle separation. And that's going to be given by something like 0.1 nanometers, so about 10 to the minus 4 microns. Now, in a cold gas, the scale is very, very different. In fact, about 10,000 times bigger, and that moves up to something like a micron. Importantly, this is an optically resolvable length scale. Now, thinking instead about time scales, again, in a condensed matter system, physics tends to happen very fast. And in particular, specifically, the characteristic time scale over which these electrons can reorganize themselves and physics can happen will be something like a femtosecond. So that's a very, very short interval in time, and so it's very challenging to observe dynamics in this type of system. Now, in a cold atomic gas, again, this is scaled up to more like tens to hundreds of microseconds. And what that means is that you can, without using any particularly advanced technology, make movies and really watch in real time the evolution of a system of many quantum particles. Now, the price you have to pay for working with such low densities is that in order to access a regime when quantum physics becomes very important, you need to get to very low temperatures. And to give you an idea of how cold we're working, what I'm showing here is a logarithmic temperature scale. So every interval on this scale represents a factor of 10 in temperature. So we're sitting in this room at a relatively balmy, 100 Kelvin or so. We're going to ignore factors of 2 or 3. And then we can just place a few of our favorite places in the universe on this scale to give us some idea of the geography that we're moving in. And again, to give it some sort of intuition for what these kind of energy scales mean, the molecules in this room are probably zooming around at something like 100 meters per second. Now, in the cold gases that we work with in the lab, we're working all the way down here at something like the nanokelvin regime. So these are, what's quite nice is they're very comfortably the coldest objects in existence. They're colder than anything else really in the rest of the universe. And again, to give some intuition of what that means practically, the atoms in our gas are probably moving at something like 1 millimeter per second. So it's really a very different state of matter. But what's nice is that we're trying to use experiments down here to learn something about the physics up here. Now, how do you prepare such a gas? Well, of course, you need an experiment, and you need to build a machine to do it. And generally, our experiments fall roughly into 2 halves. We need a lot of lasers and a lot of optics. And these are used to prepare and manipulate and sculpt the laser light which we use to manipulate our atoms, so to cool them down and to exert forces on them. And we also need a big, complicated vacuum chamber inside of which we trap our atoms, then send in laser light, manipulate them, and try to do our experiments. And so what we're setting up currently here at MIT, and what I'll be working on over the next couple of years, is a new state-of-the-art experiment to try to address some of these questions which I've introduced corresponding to the behavior of a Fermi superfluid when it's squeezed down into 2 dimensions. So this is a picture of the machine that we're building. And really all of the action takes place in this little region here shown by a red circle. And if we zoom in, what you find is this little glass cell. And inside of this glass cell, above this glass cell, is a very high-resolution microscope objective. So we have this glass vacuum cell, a high-resolution objective, and inside the cell, just below this objective, is where we'll trap our cold cloud of atoms and squeeze it down into 2-dimensional flatland by using laser light. And what we're doing in this machine is really bringing or combining together 2 of the big recent technological advances in the field. And so the first of those is the ability to start to resolve these clouds at the single atom level. And so what I'm showing in the top right is an image taken from one of the other groups in MIT, where every orange point actually represents a single atom in the cloud. And so this is a very, very powerful tool that if you want to understand how a collective quantum system is behaving, what better tool than to be able to watch what individual atoms are doing in the system. And secondly, by running this microscope in reverse, and rather than using it to take images of the atom, instead use it to project light onto the atoms, if we can sculpt and shape laser light well enough, we have extremely good control over the pattern of laser light that the atoms see, and therefore we can control extremely well the environment that they live in. And just to show how good the field has become at shaping light, this is a picture of my PhD supervisor actually built out of a laser beam. So this is a cut through a propagating laser beam, which we've controlled to have a completely arbitrary pattern of intensity. And so to give you an idea of progress, in the lab we now have our laser system set up. And in fact, this picture was taken this morning of our new vacuum chamber. And so what's nice is that this machine, as well as answering the questions I've just introduced, should be providing exciting new science for several decades to come. So with that I'd like to finish and to thank you for your attention. I'd also like to acknowledge the other members of the team, so in particular the graduate students, Bishru, Parth, Zenji, Elliot, and Cedric, Julian, one of the postdocs, and of course the PI, Martin Zvirline. And then as a final thank you, I'd like to acknowledge Jane and Neil's support of the program.
Maybe that's a question already. Okay, questions for Richard about cold gases?
Wolfgang should have a question.
So how fast do you want to rotate those atoms?
That's a question I'm very happy to have. So what you'd like to get to the regime, as I said, of roughly 1 vortex per particle. And so in a condensed matter setting, that would correspond essentially to quantum Hall physics. And so in a Fermi gas, that rotation speed is set by the Fermi energy. And so something like kilohertz. And I mean, the main challenge so far, you can ask, like, why hasn't this regime been accessed? As I said, it's an extremely interesting sort of area of physics to try to investigate. The reason is it's generally very difficult to reach those kind of rotational speeds because any roughness in your trap, once your gas is rotating, they see that as a rotating sort of roughness and rotating perturbation, and it couples to heating. And so what we want is to firstly to have this extremely high resolution control over the optical potential, and also to incorporate some kind of real-time feedback to actually produce an extremely smooth, very, very round trap for the atoms.
So I had a question you didn't, it's kind of technical. How do you ensure that there's not motion up and down? I mean, how do you ensure that it's really flat?
Yeah. So so just for clarity, what I've omitted a lot of detail here, and so I mean you can also ask the question. I mean, how do you even move these atoms around? I mean, they're colder. They're millions of times colder than deep space, let alone the room that you're working in. And so there clearly can be no thermal contact between, for example, the edges of your chamber and the cloud itself. And so what you use is the fact that laser light can actually exert a force on an atom. And so what I'm not showing here are the laser beams which are used to create the trap. And so to squeeze them down into 2 dimensions, the trick that one would tend to use is what's known as an optical lattice, which is when you interfere 2 laser beams which are counter-propagating. What you get is a standing wave of light, so alternating stripes of bright and dark, and the atoms will simply sit in one of those planes.
They're not in little potential wells where they could go up and down, or are they just cold enough so that they're...
Why are they 2-dimensional?
Yeah.
Yeah, exactly. So you're absolutely right that, I mean, most of the traps you work with is some kind of harmonic potential. Here you really have to make use of quantum mechanics, which says that in some potential, there's not a continuous spectrum of energy levels. Instead, energy levels have some ladder.
You're just cold enough so that you're not populating.
Exactly. You're cold enough that the spacing between levels in the oscillator is much larger than any energy scale in the rest of the gas.
What gas do you use for that?
So in our case, we use a gas of lithium-6, which is a fermionic isotope of lithium. I mean, the physics shouldn't really matter, depend on the atom that you're using. We're not really interested in lithium. It just turns out to be a convenient fermionic atom to do these experiments. But those are more for technical reasons.
Other questions? Okay, let's thank Richard again.